Well, in this video, we are going to spend some time understanding what is overthinking for O1-like LLMs, and this paper proposes a strategy that will help us mitigate the overthinking problem of O1-like models. So the title of the paper is pretty interesting. Do not think that much for 2 plus 3 equal to ? On the overthinking of O1-like LLMs. Now, this paper talks about O1-like LLMs, which are chain of thought processes LLMs that can process a simple question in different ways and different means of thoughts in a chain of thought process. So on the left figure, if you can see that the conventional models, for example, on the given left here, the Qwen 2.57 billion, Llama 3.370 billion, DeepSeek Math 7 billion, Qwen 2.5 Math 7 billion, Qwen 2.5 Math 72 billion. So these models, the number of generated tokens for this particular question, what is the answer of 2 plus 3? So the number of generated tokens is very less. You can see it's just the answer, it's like the 2 plus 3 equal to 5. So in order to answer this simple question, the conventional models uses lesser number of tokens. When you compare this with the O1-like models, you can see on the right hand side, the O1 preview takes 226 number of tokens for answering this simple question of what is the answer of 2 plus 3. The O1 mini takes 218 number of tokens for answering this simple question. You can see DeepSeek R1 preview, it takes a staggering 936 tokens for answering this simple question. And QWQ, which is question with Qwen model, 32 billion preview, this is another great model. It takes 901 tokens for answering this simple question of what is the answer of 2 plus 3. So I think and I feel that now you know that the problem is apparent, and it's very bad that we use a lot of resources for answering this simple question. Now, the models or the proposed strategy that this paper is proposing is to reduce the number of tokens while maintaining the accuracy. So they have done the studies on QWQ 32 billion preview, and they were able to take this from somewhere in the range of, let's say, 2400 tokens to the range of 1500 tokens, and thereby improving the accuracy a little bit as well. But for the discussion's sake, we can say for the same accuracy, their method, the method that is described in the paper, is able to reduce the number of tokens required by from, let's say, 2400 to 1500 number of tokens. And this is for the Math 500 dataset, which is a very tough dataset for the LLMs to solve. Now, this is the issue. You can see that this paper presents the first comprehensive study on the prevalent issue of overthinking of these models, where excessive computational resources are allocated for simple problems with minimal benefit. We introduce noble efficiency matrix for both outcome and process perspectives to evaluate the rational use of computational resources by O1-like models. Now, using a self-training paradigm, we propose strategies to mitigate overthinking, streamlining reasoning processes without compromising accuracy. Now, experiments show that our approach successfully reduces computational overhead while preserving the model's performance across a range of datasets with varying difficulty levels, starting from GSM 8K. We have Math 500 GPQA, it's a graduate level, Google Proof question and answers. This is another tough data sets to tackle, and AIME is another tough data set to tackle. So let's go and see the paper. So the contributions that they're putting forward is to first give a first study offering both a definitive explanation and comprehensive analysis of the issue. Now, we have already seen the issue. The issue is that even for simple problems, the O1-like models goes on thinking and thinking and thinking. They were using so much resources which is not essentially not contributing to the efficiency or the accuracy of the statements of the answers. Now they've introduced matrices considering both the outcome and process perspective to assess the efficiency of the O1-like models, and they explore several strategies to tackle the overthinking issue, significantly reducing token generated while maintaining model performance. Now, if we look at this example, this is the overthinking issue. We see that llama 3.370 billion. We see that here the answer is quite straightforward. The answer to 2 plus 3 is 5. This is like 7 tokens. Quen 2.572 billion is like 7 tokens here. Quen 2.5 math 72 billion, it's 45 tokens. You can see to answer the to find the answer of 2 plus 3, we can follow these steps. Start with the number 2, add the number 3 to the number. When we add 3 to 2, we get 3 plus or 2 plus 3 is 5. So the answer is box of 5. GPT-4o, it gives out the answer in 7 tokens. The answer to 2 plus 3 is 5. Very sweet. Gemini Pro, 5 tokens. 2 plus 3 equals 5. Claude 3.5, it gives out in 7 tokens. The answer to 2 plus 3 is 5. Again, sweet answer. But on the right hand side, you can see this is the O1-like model. It can bring out a step-by-step. It has chain of thought process inbuilt, even though it's good for reasoning tasks. But you can see for the simple problems, it gives out the answer in 901 token. Let's go and have a look at the solution that it's putting forward. So solution 1, 39 tokens, 2 plus 3. That's pretty straightforward arithmetic problem. I think I can handle this. So let's see, 2 plus 3 means I'm adding 2 numbers together. I know that when you add 2 numbers, 2 and 3, you get 5. So that's pretty much the answer, but it again goes forward and tries it in a different approach. But maybe I should think about it step by step and make sure to understand the process. First, what is addition? Addition is a mathematical operation when you combine 2 or more numbers to get a total or sum. In this case, I'm dealing with 2 numbers, 2 and 3. So starting with 2, if I add 3 to it, I'm essentially moving 3 steps forward on the number line. Let me visualize. If I start at 2 and move 1 step to the right, I reach 3. Another step takes me to 4, and one more step takes me to 5. So 2 plus 3 equals 5. Cool. The second time you're getting the answer. Alternatively, I can think of in terms of objects. Okay, suppose I have 2 apples and then I get 3 more apples. How many apples do I have in total? Well, 2 apples plus 3 apples equals 5 apples. Like, is this a game for you? I mean, it's giving solution in so many different ways. So solution 4, another way to look at it is using fingers. I can hold up 2 fingers on one hand and 3 fingers on the other, then count all the fingers together, which give me 5 fingers. Pretty cool. Another solution is I can also break it down into smaller numbers. For example, 2 plus 2 equals 4, and then I add 1 more to make it 5. So 2 plus 2 is 4 plus 1 is 5, which is the same as 2 plus 3. Moreover, if I consider the number properties, 2 plus 2 are both positive numbers and their sum should be a positive integer, which is 5. Pretty good. This is checking for the positivity of the answers, because both the problem had positive numbers, and when we add 2 positive numbers, it is again a positive number. Furthermore, in algebra, if we have an equation like x plus 3 equals 5, then solving for x would give me x equal to 2, which aligns with 2 plus 3 equals 5. Okay, another solution. Alternatively, using Roman numerals, 2 is 2, 3 is 3, adding them gives 5, which is 5. In conclusion, we can see the answer is 2 plus. So much thinking is not required actually for such a simple problem. Now what they have done is they have done some analysis of the problems that we are facing at hand using different data sets. So they have tested using ASDIV, which is the elementary school test set, GSM 8K. It has 1319 problems where any grade school math word problems, any grade school student should be able to do this. And math 500, this is a pretty good challenging data sets of high school math competition consisting of across 7 subjects: pre-algebra, algebra, number theory, and there is difficulty range. Now you can see that the difficulty ranges goes like this. Now they have investigated on 2 language models, O1 like models. They were able to get their hands on Qwen, Question Unit Qwen, 32 billion preview, and DeepSeek R1 preview. So using these 2 models, they have done some studies, and you can see that in this distribution, if you see carefully, the x-axis has the number of solutions here. The y-axis is the distribution ratio. We can see that, for example, the blue one, whenever we ask an ASDIV question, QWQ responds about 41% of the time in 3 number of solutions. Okay, so if you do this, if you ask the questions many number of times, this is the distribution that we get. So given a question, given for example, given let's say a math 500 question, the QWQ here answers, 36% of the time it answers with 3 number of solutions. So you can see that for this data set and for this distribution, a 3 number of solution is common. So you can expect that about 40% of the time you are going to get 3 number of solutions. Even that is not required, just 1 or 2 is fine. Okay, so you can see this that on the x-axis as the math level difficulty. So on the scale of x-axis, we can see that the difficulty level goes on increasing. So when you can we see that when we increase the level of difficulty, we can see that the number of solutions here, so the number of solutions goes on decreasing. Okay, but the number of tokens, it goes on increasing. So you can see that whenever we give it a very difficult math problem, then it is not able to solve in too many ways. So it's able to solve in an average of 2.9 different ways or different solutions, number of solutions, but the number of tokens is very high. Okay, because this is a tough question. Now for the easy questions, the number of tokens is less, but the number of solutions is more. So the assumption and what you're trying to prove in this paper is that we are saying that for a simple question, we don't need that much number of solutions. But do we really have that number of solutions? In other words, does my LLM answer in more number of solutions if it sees an easy question like what is 2 + 3 equals? The answer is yes. Whenever there is a lesser difficulty level of math questions, our LLM, which is the QWQ or even DeepSeek R1, it answers in more number of solutions because it's like a game for it. It's fun because it's using less number of tokens and it's an easy question, so it repeats more number of times. It gives out different ways to solve the same problem, as you have seen in this figure 2, and you can see that we have done this in 10 different solutions for this simple problem because it shows off, if I'm allowed to say that. So this is the issue. So the issue is clear that whenever the question is easy, the number of solutions is more. Now once we accept this, so this results support our claim that O1-like models tend to generate more solution rounds for easier math problems. So once we know the problem, we can now address this with our different solutions. Also, we see that on the right, the distribution of occurrence for the first correct answer. And we can see that about for 97, 95, 92, 93% of the time, the first solution is the correct, which means that the other solution, the second solution, the third solution, the fourth solution doesn't contribute much to change the answer. It's not even required, if in a simpler term. So later solutions marginally contribute to improvement in accuracy. So this is what they have found out. Well, having set the base, we can go ahead and come up with the solutions. So they are proposing these solutions. They're proposing, okay, so we have the problem again. The overthinking issue faced by online models are particularly pronounced with simpler math problems. Now we are trying to mitigate the overthinking issues. So they're proposing simplifying responses. So they're proposing three things here. So they propose three types of simplification strategies that differ on how to truncate the responses from the beginning. The first is the first correct solutions. This strategy retains the earliest solution that first arrives at the correct answer, the FCS and reflection. Since the majority of the responses achieve the correct answer on the first solution, maintaining only the first correct solution might cause O1-like models to revert to conventional LLM behavior. To counter this, we extend the approach to include a second solution that reached the correct answers in positive examples, recalling the model's long reflective capability while maintaining efficiency. Okay, we cannot leave the model with the FCS because then that would not be a reasoning model. The next is the greedily diverse solution. Figure 6 demonstrates that distinctiveness of solution 2 significantly decreases because the solution often double checks answers from the first using the same perspective. Consequently, FCS plus reflection may reduce efficiency. To address this, we proposed a simple heuristics that greedily expand solution, providing new perspectives. Additionally, this strategy includes more solutions when the second solution does not repeat the first, thereby increasing the diversity. Now they have, for each of the instance, they select the shortest result for each type of for the temp samples. And if we look at the results, we can see this is pretty good. For the accuracy, we can see that for the easy level questions, the method that they have proposed is able to improve the accuracy. Even for a difficult question as well, they're able to improve the accuracy from 83.6 to 85.7. For considering the number of solutions, we can see that the number of solutions is reduced from 3.6 to 2.0, which is what we wanted. We wanted lesser number of solutions. Even for tough questions, the number of solutions decreased. Now this is an integer because the results were carried out for a different number of times, and therefore we have this average number of solution here. Also the number of tokens, we can see that the number of tokens has reduced. Now having said that, we can see that there is an improvement in accuracy. There is a reduction in the number of solutions outputted by the QWQ, which is the LLM that I've tested, and the number of tokens also reduced significantly. Now this is what we wanted. We wanted to save cost, we wanted faster results, and we don't want our LLM to go on answering the same question, you know, in multiple different ways unless of course we ask it to do. So this is what this paper is talking about. Now there are of course some limitations. Our analysis overthinking issues was based on two models, QWQ 32 billion preview and DeepSeek R1 preview. These are the only two models that exhibit a visible long chain of thought process. So they would like to try with other models as well. We will try it out as and when new model comes up. Okay, so this is what is the issue. Again, TLDR. For this simple question of 2 plus 3 equal to question mark, we don't want our LLM to go on and solve and in different number of ways go on explaining the different steps in different numbers of ways. We want a very short and sweet answer, for example as GPT-4o or Claude 3.5. Now for simple problems, these type of LLMs, which is QWQ 32 billion preview or O1 like LLMs, they tend to respond, that tend to talk too much, and we have devised a way in order to make them talk less but talk what is relevant. In the meantime, we were able to improve the accuracy as a little bit as well. We're able to decrease the number of tokens and thereby save dollars on compute whenever we do the inference. So having said that, I will see you in another video. Thank you and have a nice day. Watch out the other videos. Bye bye.